Not a bad job, huh? Okay, so I did find the part in the Navy report from 1947 or 46, whatever it was. 4,694 welded steel Liberty ships or T1 tankers. 970 of these vessels suffered casualties involving fractures. 24 vessels sustained a complete fracture of the shrink deck. 1 vessel sustained a complete fracture at the bottom. 8 vessels are lost. 4 broke into, and 4 were abandoned after failure occurred. 26 lives were lost. The highest incident of fracture occurred during the combination of low temperatures and heavy seas, blah, blah, blah. Anyway, so there are conclusions in here. Yes?
Was it because they were making more vessels? Was it because they were making it in a different way? Was it because they were in the North Atlantic, which we didn't normally travel because we had different routes based on the submarine? I guess why did they not solve these problems earlier? Why hadn't they seen these problems really before? Was it such a surprise to them?
Well, there are a couple of reasons. One is they had never really welded ships before, okay, in this quantity, okay. They had welded ships. The first metal ship was like in 1860. All metal ship was in the 1870s or something. I can't remember the name of it. It was a big commercial liner for going across the ocean. And yeah, we had the Monitor and Merrimack, but they were just bolted and nailed on sheets of steel on the wood planking, right? And they did build the Great Eastern. Wasn't the Great Eastern? It was all metal. But they built an all-metal ship in the 1870s, and then warships in the Spanish-American War were steel, but they were all riveted. They didn't have welding technology. Welding technology did not come about until we had a cheap source of electricity. And when was that? 1880s, with guys named George Westinghouse and Thomas Edison. Okay? Arc welding was invented by Sir Humphrey Davy in the early 1800s, like 1805, 1806, when he discovered the electric arc. And the reason it's called an electric arc is because it had 2 probably copper electrodes that were horizontal, and he was using electricity from a Leyden jar or some sort of battery or something. He pulled it apart, and he struck an arc, and it was luminous flame, but it had an arch, because the rising gases created an arch. And that's where the word arc comes from. It's a welding arc. And one of the first things he did with his new heat source was he welded. Okay? But no one could do it commercially until the 1880s on a large scale. There's a woodcut in a lot of the welding books on the history of welding. It shows a battery of Leyden jars in the background and a French woodcut showing people welding in the 1850s or 1860s by electric arc welding. But really, electric arc welding didn't exist in a big way until the early 1900s, and there was a lot of work done by companies to build welding power supplies, arc welding power supplies, and then to develop what we call stick electrodes. This is actually part of one of the other ones we'll probably watch on video, but I might as well tell you some of the history, because I'd much rather hear a question than just give you my lecture. So this is a stick electrode. What happened is originally people were just welding with a bare steel wire. Okay? And the problem with the bare steel wire, when you arc weld, is it picks up nitrogen from the air, and when it solidifies, the nitrogen gets rejected. And the rejected nitrogen comes out and makes the weld porous. Looks like Swiss cheese. I mean, not small pores. These are things the size of a BB or something like that. And it's just a terrible looking weld. It has some strength, but it's not as strong as it should be, and it looks terrible on the surface. So, turns out 2 things happen. There's 2 types of electrodes. One guy in Göteborg, Sweden, working for a company that's now part of what's called ESAB Corporation, found that if he stuck his bare steel electrode, this is in the early 1900s, stuck it in the mud and welded with a muddy electrode, the porosity went away. And that's the basis of what we call mineral-coated electrodes now. This is a 7018 electrode, common high-quality welding, low hydrogen. It's got a kind of a cement-like coating, flux on the surface. If you bend it, it will start cracking immediately, okay? You can bend it all you want, I'm not gonna use it now. But you can pass it around, see how brittle it is. Another guy in the United States, and I don't know who this was, but he found if he wrapped his electrode in a piece of paper, he could weld, and he no longer got the nitrogen porosity. They didn't even know it was nitrogen porosity back then, but that's the basis of what we call cellulosic electrodes. You bend it a lot more before it starts to crack. That one's heated up to about 350 degrees Fahrenheit. That one's heated up to about 800 degrees Fahrenheit to drive the moisture off. Okay, this one, full of moisture. They make it out of paper. Actually, they don't make it out of paper. Lincoln Electric uses old tobacco stalks as their form of cellulose. This is proprietary information. I got it out of the gutter. Okay, I didn't get it from Lincoln, but I'm told they use old tobacco stalks. I got it from one of Lincoln's competitors. Okay, who was just telling me the story once. Because tobacco concentrates the rubidium from the soil, and rubidium's in the first column of the periodic table, and rubidium is being in the first column of the periodic table, gives up electrons much easier than sodium or potassium. Okay? And so, what could be cheaper than old tobacco stalks, which have no other use? Okay? And you get a cheap source of rubidium too, which helps the arc stability. So there is some science to it. But in any case, in 1900, people learned to make stick electrodes, but they still didn't have really good quality welds. And in World War I, there was a professor at Harvard named Comfort Avery Adams. He was known as the Dean of American Engineers. And as we entered the war, he was put in charge of the Emergency Fleet Corporation, which is a new part of the federal government, to build the ships to get the boys over there. Couldn't fly them back then. You had to float them, okay? Well, they riveted the ships. But Comfort Adams was actually one of these, he was an electrical engineer, and he worked on building welding power supplies as part of his career. And he realized after the war, they had never been able to weld the ships because they didn't really have the technology. So he decided in 1921 to form the American Welding Society. He was the first president of the American Welding Society. He gave the Adams Lecture of the, he was the first Adams Lecture, named after himself, but the society, he was the leader of American welding at the time. Well, they didn't build a critical structure by welding until the early 1930s, and they built the big inch pipeline. This was a gas pipeline coming from Louisiana up to New Jersey, 30-inch diameter. Now, they had built pipelines before, but they were riveted, same overlaps, and very intensive. I mean, back then they didn't have automatic riveting guns. They had people with hammers, okay, and arms, okay. But they wanted the leak-tight joints, and they built the big inch pipeline. Okay, 30-inch pipe from Louisiana. And it's critical. I mean, if you have a high-pressure gas pipeline that explodes, it's not a good day. And then in World War II, they had to weld the ships. They couldn't build 5,000 ships with a bunch of people riveting. I mean, there may have been Rosie the Riveter, but she was building aircraft. Okay, because they were made out of aluminum, which is even more difficult to weld. Okay, so they welded the ships. So to answer whose question was it? Your question. Why did we run into all these problems? It was the first really massive use of welding of steel, and they didn't really know how to do it. And in fact, since we're talking about that, I can tell you another thing we don't know how to do anymore. In general, this was a little harder to pass around, but this is a weld. I will pass it around. This is a weld in a 17-inch thick piece of steel. It was part of the forging press they were trying to repair in Pennsylvania some time ago. I didn't count exactly. It has somewhere between 400 and 800 weld passes in here. So little weld passes made by stick electrodes. It weighs a little bit, but don't touch yourself. It doesn't have really sharp edges. But anyway, you can look at that. That's how they welded battleships in World War II. One little stick electrode at a time. 4 to 6 pounds an hour is what a welder can put down. And what did they do? Sometimes they were tired and they would slug the welds. Anybody know what slugging a weld is?
They build up, like, it wouldn't be an even bead. Some of the beads
It
would be
wouldn't be
soldered.
an even bead. It'd be on a big thick thing like this on a cruiser or a battleship. So they take a bunch of electrodes, drop them in the groove, and weld over them. Talk about a critical flaw size, okay? And that's not a good thing. I've only seen one slug weld in my life, okay? We tend to know you don't slug welds. That was on a maritime thing. It was actually here on what's the highway south of Boston on Interstate 95. There's another one, 28, Route 28 next to it, which is like an interstate highway. And this guy was from Canada, Nova Scotia. And he had this 40-foot sailboat. He'd gone down to Newport to the sailing races. He won the championship. And he's driving back home to Nova Scotia. He's got this home-built trailer that's got the boat. And he hears this, as he's cruising down the highway, hears a big bang. And of course he puts his brakes on, and he sees this boat go by, just like his. Okay, it was his, okay? The trailer had broken in two, and his boat was cruising down with no brakes, okay, and destroyed his boat. And it turns out someone had slugged the weld. The weld, someone took a bolt between two of the angle irons and stuck it in there and welded over the bolt. Yeah, you wouldn't do that in Newport News, would you?
I was just going to say, so, this is just a C story from my experience there, but like even welding by hand can cause imperfections that cause flaws in these weld joints, and this feels like this thick, which are the hemi heads of the submarine. And
You can't
so,
tell us how thick it is because the other side will know how deep it can go, so
Right.
be careful. Okay.
It's right? This is a very non-technical matter. So it's very, very thin. And so, and that's for the hemi head, which you can't put frames in the hemi head, especially towards the caps. And it's made out of 3 big pieces of steel. So you take 3 triangles and you mesh them together, and it makes a dome, a curved piece of triangle. And so they don't have guys handling them. What they do is they put them in these fixtures, and they build temporary railroad tracks across the stitch, really, right? And they put a automated, mechanized, gear tooth mechanism welding machine, and they have a guy who's trained to just walk along with it. And so he just walks it, and then just marches back and forth across this welding. He adjusts every time, and it lays a consistent bead down. And there's several hundred beads that go into this, because it's a V notch like this, it's really thick. And of course they flip it upside down. They back gouge the back of the weld out, just to make sure they have a clean surface to weld through. And then of course when it's in a bowl, they actually have a fan down there so that they don't get an accumulation of like inert gases and something can pass out down there and whatnot. And then they do this exact same thing on the reverse side, and then of course they buff it out and smooth it, and then it kind of rolls down the line. So.
And you can't have a defect bigger than 3 millimeters in there.
Yeah, and so they
Or
do
they have
all
to
their
dig it out.
various different NDTs for those different welds and stuff, but they just crank them out. They put those pieces of metal, and there was always something being worked on, flipped one way or the other, rolled down the line, and then those eventually go get holes cut in and all that kind of stuff. So, anyways.
So, thank you. That's a good story. To talk about some other submarine stories. Anybody familiar with the torpedo tubes? And they have to be very straight, right? And they're pretty long. Okay, they're longer than the torpedo, right? And they have to be. I don't know what the tolerance is, but it's like a millimeter on the length. Okay, and they used to weld them up, and of course you get distortion from welding. And then they would machine them with a great big boring machine that would go the length of one of these things. And I don't know how long they are, but I'm sure they're probably 40, 50 feet long or something. And it was my first student who went to work for Electric Boat. He's now retired. I'm still working with him. He figured out how to do it so that they would not have to straighten them, okay? And basically, when they put the welds in, just like you were talking about going around, they actually had the thing on rollers, and so they would just weld it and go around. But basically, he put some feeler gauges, or not feeler gauges, but not torsion gauges, but just the ones that just measure distance, spring-loaded distance gauges, okay, on the end, a couple of feet away, and he could see the angular distortion. And what he would do is he would compensate with the weld, and he would stop the continuous weld and go on the other side to pull it back the other way.
Right.
Or if he had to, he'd actually grind out a weld and put another weld in to cause more distortion in that direction. So he monitored in process the distortion and corrected for it in this cylindrical joint. And all of a sudden, all they had to do was just do a skin pass down the bore, as opposed to taking, you know, a 1/4 inch off or whatever.
So I don't have a very deep materials background, but that was one thing that blew my mind at the shipyard, is that all the welding is like, metal's like paper in a shipyard. So if you like, you know, you fold it and those kinds of things, and it warps and bends as you do things to it. So like the shell, like the hull itself will distort and bend. So the whole, they have these, they're, well, we call them C-clamps, but you basically spot weld a bolt like a kind of like a metal peg on there, and you can attach a C-clamp to it, and the clamp like screws onto this tack welded bolt, and then you can screw it up or down along that bolt, and it has this, you know, it's a curved portion. So if you imagine like here's a seam of 2 pieces of metal like this, then you have this thing bolted here, and it presses against this piece of metal, and it goes all the way around the circumference like that. And so you have a whole thing like orange, right? So there's a whole bunch of orange clamps all the way around the whole circumference of this weld joint. And then you kind of, you use a air power jack, and then you it's like the, I don't know if you've ever heard it before. Anyway, you can warp this whole cylindrical thing within tolerance. You hold it in place, and then you weld it all, and then you can take it all. And so this whole thing is under stress, right? Like the rest of the submarine's life, there's some degree of inherent stress in the metallic structure, because you had to line this up, you know, within an exact tolerance in order for this whole cylindrical thing to line up. And that's done, since we build submarines in pieces, that's done down the entire length of the submarine. Every module is kind of lined up and fit like that.
Yep.
So he was on the build side of it, I was on the repair side of it. So when you, we have a lot of corrosion issues with carrier nuclear piping that we're dealing with right now. So like back in the shipyard when they built the thing, they would jack a pipe, you know, it didn't line up, so you jack it over 3 inches and weld it, and now,
when it corrodes, it goes into the
20
way.
years later, we cut that pipe out and realized you can't just rebuild it and have your piping line up with no stress. So now you're refabricating entire piping systems with pretty complicated processes to weld it back together, because it was easier to just crank it over a few inches and weld it.
Yeah, I mean, there's a lot of brute force that goes on in a shipyard. This is kind of what you're talking about. You have your 2 pieces of your hull, and they're not matched. So you basically weld this guy on, have a screw on here, and you press this one down and pulls this one up, and you bring it into the alignment. If you look at manufacturing tolerances, a typical manufacturing tolerance, and it doesn't matter whether you're talking semiconductors, you know, silicon chips, or ships, a typical tolerance is 1 part in 2,000. So if you're a machinist, and if you've ever worked on a lathe, and you're trying to machine something to 1 inch diameter precisely, you can get about half a thousandths, 5/10,000ths of an inch, without too much difficulty, using a little micrometer and stuff. You can machine it to that tolerance. That's a typical tolerance, and it doesn't matter. But if you talk about a ship that's 1,000 feet long, that's a 1 inch distance. If you're off by an inch, the holes don't come together, okay? So it turns out shipbuilding is, I used to be able to say shipbuilding, and I learned this from Dan Whitney, who's over in the mechanical engineering department. He pointed this out, this whole tolerance thing to me once. Shipbuilding was the most precise manufacturing that we did in terms of parts per thousand. You're about 1 part in 20,000 in terms of the tolerances you have to put. And then when the sun comes out, or the cloud goes in front of the sun, the whole ship changes its shape, okay, just from the solar heating. And you have to weld these things so that there's not a bunch of mismatch. Yeah.
I was the docking officer at the shipyard before I came here, and we dealt with that a lot. Like, you build a carrier that's 1,000 feet long, and then you got to dock it on wooden blocks. And you after you dock it, you see the thing, like you're saying, the sun comes out and the front end of the ship lifts up because the temperature just warps it. It's just crazy how.
Down in Pascagoula, they actually have some huge shades, I've heard, I haven't seen them, that basically, when you're welding out there in the hot sun and stuff, it gets hotter down in Pascagoula than some other places. They basically have to control the solar heating. Are we? Seen it?
Yeah, I said hotter than hell down there.
Okay, so, in any case, so there's a lot of little different things in welding that you have to worry about.
One more fun fact, I'm gonna throw it out. It's kind of neither here nor there, but I thought it was really cool when I learned it. But that jack clamp, it also has a chain attached to it. Because I always wondered why the chains were attached to every single one of those. There's actually a chain attached to a linkage. I was like, why is this chain here? And the idea is that if that's, you get welded, you spot welded this threaded bolt onto the side of the hull, which is then later being removed, right? But if that weld fails, and that's under pressure because you've aligned the holes, the bolt will explode across the whole, like, you know, maintenance facility, and you could like blow someone's head off with that kind of force. So it's on a chain to catch that in case one of those spot welds fails.
Of course, the only reason they do that is because it did happen once. Right? Okay, so.
Can I fish for a story?
Here.
I'm sure anyone who's worked in a shipyard, you find out that guys, you know, put a lot of effort, built a brilliant design. You know, the guys who did job instructions, brilliant detailed job instructions, goes down there and the guy who's actually on board goes ahead and uses a come along to pull a pipe against another pipe. Or do you have any stories about something that was done at the pointy end?
I'm not sure exactly what the, I know I don't have a story of a come along thing, but I was going to tell a Boeing story, okay, about fit-ups. Now, they're not dealing with plate that's 2 or 3 inches thick. And by the way, at Quonset Point, when they have they're welding the hull sections in the vertical, does anybody know why you weld them in the vertical? You're making a cylinder.
Because it's not going to flex down by its own weight.
Now, that's one of the reasons, but the more important reason is you can make 4 welds at a time. When you're horizontal, you can only make 1 weld at a time. When you're vertical, you can make 4 welds at a time. Even though each weld goes slower than the horizontal weld, making 4 at a time is faster than make 1 faster. Okay, and you also get better residual stresses and less distortion and stuff. But when they do that, they have to cover the top so that the Soviet satellites can't measure the thickness of that hull. When I heard that, this was 25 years ago, I thought, they're pretty accurate from 100 miles up, right? To be able to measure the thickness. Because they want to know that thickness within a quarter of an inch. Because any structural engineer can figure out how deep that sub can go if they know the thickness of the outer shell.
Newport News had some engineers who briefed Admiral Whitney like a year ago, and no, it was Admiral Johnson. And they basically had some pictures of some Russian submariner had posted on his blog. Like, here's the commissioning of the submarine that I'm attached to. Isn't this awesome? And you could see they had some bunting and like tarp hanging over. It's like a big, you know, take a cross section of a submarine, unfurl a big curtain over the top of it, and then stand in front of that with the podium, right? But they were like one flap of the curtain was up, and you could see like they have a double hull construction on Russian submarines, and so you could see both of the hulls there, and so you could see the thickness. And so the brief to the admiral was, this is what we perceive the kind of weapons, like damage that our weapons would do to their submarines based on the hull thickness and assumed depth of operation and stuff like that. And they were showing like bubble formation and collapse against the hull for like the damage that would cause. And it was just crazy the amount of computer simulation you could do just from taking off the thickness of the hull. Yeah.
So I mean, sometimes you're thinking, well, why is such and such classified? And it turns out you can figure out why. Now, let me tell the Boeing story. So Boeing has a spec about fit-ups, okay? Now, this is not come-alongs. This is sort of a Boeing spec. Boeing has a spec that when you're building an aircraft, and you're going to rivet the hull to the inside ring-stiffened, it's a ring-stiffened cylinder, just like a submarine, it's not quite as thick, and it's made out of a lighter material. The amount of force you can apply to bring those two into registry before you make your rivet has to be 5 pounds or less. That's the general spec, okay? And this is one of the problems Boeing has. They have general specs. They like to write general specs. And sometimes a general spec doesn't really apply to a particular application. But nonetheless, they are so worried about fatigue and residual stresses on the skin of that aircraft, they basically, the structural engineer said, in manufacturing, you have to form it so that it fits together, you know, within a few thousandths, that you cannot apply more than 5 pounds of force to bring them into alignment. Okay, so they do things, but they can't apply more than 5 pounds. You're applying more than 5 pounds on your things in the shipyard. Okay, there are different specs for different applications. In that case, they're worried about fatigue and the residual stresses around those rivet holes. In the Navy's case, you just want to make the thing fit together, meet the budget, right? And then when you come to repair it, you're lucky. I mean, I've seen situations where someone cuts something and the whole thing goes flying, okay, because of the residual stresses that are locked into the thing. I've never seen anybody get hurt from it, but I've seen some cases where some people were really shaken up because they knew they could have been hurt. And I'm sure are cases where people have been hurt pretty bad. So come-alongs are great, but they're introducing spring tension into the thing that not everybody is going to be worried about later. Okay, so let's actually start talking after 2 hours of lecture about welding metallurgy. And actually, we're not going to talk about welding, we're going to talk about metallurgy in general first. And one of the students last year said, well, at first I'm going to, he asked me the question, why are there so many steels? Well, we're going to get to that. But first we have to answer the question is, what is steel? Anybody know the technical definition of steel? Steel is an alloy of iron and carbon. And if you go to the metallurgical literature, you'll find a phase diagram for iron and carbon. This was the aluminum copper phase diagram I showed you a little while ago. This is the iron carbon phase diagram. And if you look down at the bottom, which you can't read, but has the name John Chipman. John Chipman was the guy who developed this diagram in 1973 or so. John Chipman was the department head. Our department headquarters is called the John Chipman. Okay, I knew John. He was actually retired when I came as a student. But he developed this diagram. And in fact, when we talk about steels, and they didn't have the same quality steels down back in the old days as we have today. John Chipman came to MIT in the 1930s. He was a physical chemist from Georgia Tech, wonderful gentleman, southern gentleman. And John basically used the principles of physical chemistry to high temperature melts of steel. So rather than aqueous solutions, which is what physical chemists like to study, he applied physical chemistry to 1500 degrees centigrade steel melts. And a lot of this was done in the basement of Building 8 over here. John Chipman worked on the Manhattan Project. He was developing ceramic materials that they could melt uranium and other reactive metals, uranium type. Because the uranium and or plutonium would react with any oxide, so he was actually working on sulfide materials, crucible materials. But John Chipman developed the technology to make steel reliable. And I mean, I've heard stories I won't go into, but some of his books or treatises will be found in Chinese libraries enshrined in plexiglass, you know, because this is the seminal volume that taught the world how to make steel. And steel is usually, carbon steel is defined as, by the American Iron and Steel Institute, is an alloy of carbon, iron, manganese, sulfur, and phosphorus. And it may also have silicon. Okay? Well, the iron and the carbon, it's not going to be steel unless it's got iron, and iron's the high toughness, high strength material. Carbon is there because carbon can give iron exceptional strength. And in fact, the phase diagram here, this is iron going up here. I'm going to zoom in a little bit more. This is temperature This is 1500 degrees. This is the vaporization, the vapor pressure of iron curves as a function of the carbon. This is graphite melting at 5300 degrees, or subliming at 5300 degrees. Steel is right down in this corner. Cast irons are over here. This is the low melting, just like the aluminum copper eutectic. Eutectic means low melting. A cast iron has got like 3 or 4% carbon in the iron, and it melts not at 1500 centigrade, but around 1200 centigrade. Okay? A lot easier to melt cast iron. We've been making cast iron for thousands of years, but it wasn't until 1856 that Henry Gusmer taught us how to melt steel. All the steel that had been, where did steel come from before 1850s? It either came from meteorites, which meant fairly valuable, fairly rare, but they would take meteorites, which are iron-nickel alloys, and they'd beat them down into swords and stuff. Or they take iron ore and they would reduce it with a lot of carbon in a rarefied atmosphere, and they would get carbon monoxide to take the oxygen out of the steel, or carbon to form carbon monoxide, and you get sponge iron. You're basically making solid state reduction, and you get this porous, spongy iron. The Japanese were doing it 1,000 years ago. The people in Damascus were doing it 2,000 years ago. India used to make steel, and that's where the steel sword blades of all the, the Huns and the Persians, and they had steel, but it was a very laborious process. You'd end up with spongy. I mean, it looked like, if you ever seen pumice from lava, okay? It'd be 50% air, and a guy would forge it in the forge. You just hammer it until he knocked all the air bubbles out and welded it together by just forging it together.
Well, really, so in a broad context, like to be able to make steel, like that really didn't happen until the application of like fossil fuels, right? The ability to heat something to that.
It wasn't the fossil fuels. I mean, you can't melt steel with fossil fuels. What you have to do is you have to preheat the steel. The Bessemer converter looks something like this. A little lip like this. You turn it halfway on its side, you have the molten iron carbon down here, and actually you put cast iron in here, which is 3 or 4% carbon. To make it into steel, you got to be less than 1% carbon. You got to burn the carbon out. And they knew they could do that because they'd made wrought iron for years by blowing oxygen in here. But then you blow the oxygen in, and as the wrought iron, the melting temperature would increase as you get rid of the carbon, and it would solidify on you, and basically make wrought iron. They made wrought iron up here at Saugus Iron Works in the 1630s, okay? But it was a very inefficient process of heating, reheating, getting the carbon out by oxidizing it away. What Bessemer learned is if you blow the air in such a way that, actually don't blow it in this way, you blow it in this way such that the exiting gases preheat the incoming gases. You now can get temperatures. I mean, hydrocarbons burning in air will get you to about 2,000 degrees Fahrenheit. Okay, 1200 centigrade. 1200 centigrade will not melt low carbon steel. There's 1200, you're still in the solid range. Okay? To get that extra 300 or 400 degrees, you have to preheat the incoming air. And that's what the Bessemer converter did. By bringing the incoming air in this way and the outgoing air this way, there was a counterflow, very inefficient counterflow, but you basically preheated the air coming in. So this air that got down here to burn with the carbon was preheated already to 400 or 500 degrees centigrade. So now I can get 1500 degrees centigrade in the bath and keep it molten. And after that, and since you guys seem to like some of the stories and I enjoy telling them, we came up with, Andrew Carnegie came up with the basic open hearth, which is what you'll learn if you read George Leonard's 1960s Welding Metallurgy. You could have basic open hearth steel. Today everything's basic oxygen furnace, and I'll talk about that. But we might as well spend the last little while just talking about how you make steel. up from Andrew Carnegie in the 1880s. Andrew Carnegie was the richest man in the world. He was richer than Bill Gates in cost of dollars. And he got it all on steel and basically the railroads, making steel for the railroads. He was worth $100 million, but that was more than $100 billion today. Okay? So what they had is they had an open hearth furnace. And an open hearth furnace is nothing more than a big ceramic lined pot, and basically this thing could be 50, or it'd be half the size of a football field. And you could put in a thin layer of cast iron, iron carbon alloy from your blast furnace, and you put a top on this, and you blow the air in to burn the carbon off, to take the 3 or 4% carbon cast iron down to 1/10% carbon to make
What's the
steel.
oxygen binding to carbon make CO2 or something, or what?
Make CO, carbon monoxide. So you get a lot of carbon monoxide. But a basic open hearth would have something just as large, actually two of them, just as large on either side, which were nothing more than a bunch of ceramic bricks with holes in them. They were stacked in a lattice arrangement. And there'd be one on this side, and there'd be one on the other side, just stacked up ceramic refractory brick. And to fire this thing up, you would take some natural gas or whatever, and you'd heat up the brick. This would be half the size of a football field. So the whole thing's 1.5 football fields. And it'd be stacked up several stories tall. You'd heat up the brick, you'd then blow the air through here and into the furnace so it comes in preheated. The brickwork was only to preheat the air. And the exit gases would go out through this one, heating up this one, and you'd run it for 6 hours that way, and after 6 hours when that one's cooling off, that this one's hot, you'd flip the air. And you do that 3 times, and after 1 day, you tap off 300 tons of steel. Okay? You had to preheat the air. That's how we made steel for the first 100 years. And then some guys in Europe, in Austria, decided to go back to something similar to the Bessemer converter, only, and they would have, this would just be a huge vessel, about 4 or 5 stories tall, steel vessel, lined with ceramic, okay, so it wouldn't melt through the steel, because molten steel would obviously melt the steel shell it's made out of. But you have a bath of steel, maybe 3 or 4 feet deep here. You'd pour the hot cast iron in here, molten cast iron in here, and then you bring in a lance of water-cooled copper, it might be about 3/4 of a foot in diameter, and you blow at supersonic velocity liquid oxygen, pure liquid oxygen through there. And that would create a froth of steel that would fill up the other 75% of that vessel. Just, I mean, and in 20 minutes, you can do what took 24 hours in a basic open hearth. On a basic open hearth, it was surface diffusion. It was air going across the surface. You got a boundary layer. You had to transport that carbon, the oxygen one way and the carbon dioxide the other way. Slow process, low area of contact. It's a surface reaction. Over here, it's like shaving cream. I mean, you got lots of surface area, right? And you got it's pure oxygen. You don't have to add any heat to this. You're burning carbon in there in 20 minutes. Okay? They can take cast iron, 300 tons of cast iron, turn it into 300 tons of steel in 20 minutes. Okay?
All that oxygen?
Pardon me?
All oxygen in the steel doesn't pose an issue.
If you get down low enough in carbon, but it's only when you get down to less than 0.1% carbon. The carbon will keep the oxygen low until you get very low carbon. And then if you get very low carbon, like this, it gets really expensive to get the last part of the carbon out of there. And for stainless steels, we have to get the last part of the carbon out of there. So if you went down, anybody seen where the glass lab is in the basement of the building before? That's the room where the original research was done by a guy named Krivsky in the 1950s in his doctoral thesis with John Shipley. where he was studying just the carbon monoxide reaction. And so he had a bath of steel, and they could bubble oxygen up through it to understand the carbon monoxide reaction and measure the off gases and stuff. But he wanted to get to even lower pressures of oxygen, so he started bubbling argon with a little bit of oxygen, because he wanted to have less than 1 atmosphere of oxygen. So he just diluted it with argon. And he was able to do his research on low carbon concentrations in steel. And then he went to a company called Crucible Steel to work, and they got together with a company called Union Carbide and some others. And they found, they did it, actually they couldn't get any big steel company to listen to them. They found, I think it was Crucible Steel or Sharon Steel or somebody, small steel company that was willing to take a vessel and modify it, because these are real production vessels, and blow argon and oxygen, a mixture of argon and oxygen, through the bottom of this steel bath. And it's now called argon oxygen decarbonization, AOD. All 5 million tons of stainless steel, or 20 million, whatever it is in the world made today, it's made by this process. Stainless steel has 1/3 the price that it would have had in the 1950s, before Krivsky took his doctoral thesis from MIT and applied it in industry. AOD was not invented at MIT, but the scientific principles were done by John Shipman and Krivsky.
So real quick, so carbon makes iron very strong, that gives us steel.
Right?
How does taking as much possible carbon as you can out of steel make steel better?
We're going to talk about that, and I don't have time in the next 7 minutes. But in fact, steel is unique among a lot of metals. Titanium has the same advantage. It has a different crystal structure at low temperature, which is called body center cubic, than it does at high temperature, face center cubic. And I can demonstrate that later. But because of this, it goes through a transformation, a solid state transformation at 723 degrees centigrade, if it's 0.8% carbon. If it's 0 carbon, it would be at 910 degrees centigrade. That's what this solid, actually it's a solidus line, not a solidus line, but a solidus line. And it turns out, well actually I probably can't show you. The strength of steel is a very strong function of the carbon content. And here's the plot. Some of these things will be in Stellar eventually, hopefully today. This is out of a book called Steels by George Krauss, who was one of Morris Cohen's students, his doctoral thesis here. He's retired from the University of Colorado School of Mines, used to be at Lehigh University. But he's Mr. Steele today. The guy who was Mr. Steele before that was Morris Cohen, who was an institute professor here. After World War II, when they had all the Liberty ships crack and things like that, there were 3 places that did the study based on this Navy report I showed you. One was MIT and Morris Cohen on brittle fracture of steels. The other was the Naval Research Laboratory, a guy named Pellini at the Naval Research Laboratory. And we'll talk about Pellini. When he retired from NRL back in the 80s, he came and spent the last couple of years as a lecturer over here in Course 13, which is 2N now, and then he retired on Cape Cod. The other place is a place started in 1947 or so by a guy, Richard Weck, who was a young engineer in England pedaling through Cambridge, and he was driving, I remember him telling the story about riding his bicycle into this little town called Abington, and he decided this is where he should build the British Welding Institute, Research Institute. So the 3 places in the world that really studied in the late 1940s brittle fracture of steel, which is one of the things that caused all these ships, along with poor quality steel. The poor quality steel, if you have too much oxygen, you don't get the oxygen down, and one of the ways to get the oxygen down is you throw some silicon in, or some manganese, or some aluminum, to get out that last oxygen. So first you take cast iron, which is iron and carbon, then you got to get rid of the carbon by blowing oxygen through, then you got to get the oxygen down to get the toughness up. okay? There's a whole series of processes, and we'll kind of go through some of those. But Morris Cohen was the guy here. Krauss was one of his students, and this comes out of his book. This is the carbon content versus the hardness of the steel. And you can see up to about 0.6% carbon, you have a tremendous change in strength or hardness of the steel. And then it tends to get law of diminishing returns over here. So what we're going to learn tomorrow is the difference between hardness, hardening, and hardenability. To a metallurgist, they're very different terms. Okay? Hardness is how hard it is, how much it resists indentation, how easy it is to deform. Hardenability is how deep you can do that and how we change that. You have a question, Adrian?
I'm just curious what that shaded region is.
I'd have to look. Crosshatch area shows effective retained austenite. I'll tell you what retained. Retained austenite is the part, the FCC structure that didn't transform at room temperature. Only George Krauss would get into those details. Yeah, no George, the nerd. Anyway, one of the most important things about steel, and something made it unique, and something that I did my junior year humanities term paper on in my course here, was the hardening of steel. Okay, you can take the same steel that's just as it comes off the mill and it's relatively soft, or you can take it and you can heat it up, quench it, and temper it, and you can make it into something like a file, and I can file down the corner of this thing with another piece of steel. But this one's been hardened, this one is soft. And the ability to transform, shape something when it's soft, and turn it into something that's hard is the ability to make a tool. We do the same thing with pottery. We take clay, which is soft, we heat it up, and we turn it into a ceramic, which is hard. Brittle, but hard. Okay? So we do this. This is a fundamental ability of making tools that humans have that even apes who might use tools, they just take stone, which is hard. They don't know how to transform the material into something that's hard. So I actually wrote my thesis on it, not my thesis, but my junior year paper on the history of hardening of steel. And there's interesting ways over the years. The Muslims during the Middle Ages thought that the best way to quench the steel, heat it up until it's red hot, then you ordinarily quench it with water or oil. They like to take a Nubian slave, a living person, and run the hot steel right up through them to quench it. They felt it gave spirit to the sword. So if you want a short-term profession, you can be a Nubian slave and be the quenching medium for the hot piece of steel. Okay.
Like a sword or something?
Yeah. They take the hot sword and better to quench it in blood than water. Now we just use brine. We don't need the blood. We find the red blood cells and white blood cells don't add much to it. We tried it. Yeah. Okay. Thanks.
So, on that note,
Check the card now, right?